sequences. So a sequence can be thought of a list of numbers written in a definite order. So it's ordered list. So A1, A2, A3, A4, all the way to AN, and so on. But it's we're going to be dealing with infinite, so I'll get to that in a bit. So the number A1 is called the first term, A2 is the second term, and in general, AN is the nth term. We will deal exclusively with infinite sequences, and so each term will have a successor AN plus 1. So you're always going to have further and further. And notice that for every positive integer n, there is a corresponding number an. And so a sequence can be defined as a function whose domain is the set of positive integers. And we usually write an instead of the function f of n for the values of the function at the number n. Yeah, so it's pretty much a function, but for positive integers, but we write it this way instead of f of n. Alright, so if we look at the notation for sequences, we'll have this, the sequence bracket A1, A2, A3, it keeps going on, and then close bracket can also be denoted by, or is also denoted by, writing it as like this, bracket AN, and then close bracket, or you could write it as AN, close bracket, and then you can include the parameters. So you can have it from n equals to 1 up to infinity. So this just illustrates that you're starting from 1 and then going to infinity, and these are all infinite sequences that we're dealing with. Yeah, so for the most part in this video, if these parameters aren't included, we'll just assume they are. You can just write that down like that. It starts from n equals 1 and all the way to infinity. Alright, so now let's look at a quick example, example 1, to illustrate dealing with this notation of sequences. So some sequences can be defined by giving a formula for the nth term. In the following examples, we give 3 descriptions of the sequence. One by using the preceding notation, and then that's this one right here. And then I'm going to write the other ones down myself. So this one, circle this. These ones we'll do right now. So another by using the defining formula, which is the one inside. And the third by writing out the terms of the sequence, writing it all out. So for the first one, for number A, we have n over n plus 1. And then from n equals 1 to infinity. So we'll have an, the defining formula is just an equals to n over n plus 1. And then we could also write this out. So if we were to expand this out, just expand this out, we'll have at n equals 1, we have 1 divided by 1 plus 1. That's just 1 over 2. And then when we have 2, and then 2 over 2 plus 1 is 3. So 2, 3, and as you can see the pattern, it just goes higher. So 3, then divided by 4, and so on. So then it's going to be 4 over 5, and so on, dot, dot, dot. And then it's going to add the term there, n plus 1, and keeps going on, close bracket. And now for B, for the same thing, we have right here, so the an is going to be the inside bracket. That's going to be negative 1n, n plus 1, and then 3n. So we're going to start again with n equals 1. If it's not there, we just assume it's, we're just going to be defining from n equals 1, from the first term. So we have n is 1, so when we have negative 1 to the power of 1, that's going to be, well, negative 1. It's an odd number. So negative 1, then we have 1 plus 1 is 2, so we'll have a negative 2 over, this one's 1, so 3. And then the next one we'll have, well, 2, negative 1 to the power of 2, that's positive, so that it's not going to have a negative sign. So if it's positive, make this thicker. So it's going to be positive, and then we'll have 2 plus 1 is 3. So positive 3 over 3 to the power of 2 is going to be 3 squared, and that's just going to be 9. And then going further, now when we include a, so the third term's 3, so negative 1 power of 3 is an odd factor. I'm not odd power, so that's going to be a negative. And then 3 plus 1 is 4. And then 3 to the power of 3, that's going to be, well, 9 times by another 3, that's going to be 27. And then next one up is 4, so put that, that's going to be even power, so it'll be positive. 4 plus 1 is 5. And 3 to the power of 4, well, that's just going to be, times by another 3, it's going to be 81. You could also see it as, I'll put this like this, 3 to the power of 4 is just equal to 3 squared, which equals to 3 squared times 3 squared. In other words, we're just having a 9 times 9. Or a 9 squared, so equals 81. and so on. Then this goes dot dot dot, and then we'll have negative 1n, n plus 1 all over 3n, and then this is going to be, keeps going on dot dot dot, and close the bracket. Alright, so now let's look at C, which is over here square root n minus 3, then from n is equal to 3 all the way to infinity. So we have the an, the defining formula is one inside, square root n minus 3, and then the terms inside this are, so when we have n is 3, we'll have 3 minus 3 is 0. So 0, square root of 0 is still 0, and the next one up we have 4. 4 minus 3 is 1, square root of 1 is just 1. Next one is going to be 5. 5 minus 3 is 2. So we'll have a square root 2. And the next one we'll have a 6, square root 3. So 6 minus 3 is 3. And so on. It just keeps going on and on. And you can just put a square root in all of these. It won't change 0 or 1. But we keep going on, and then we get to square root n minus 3, and so on. It keeps going on and on. And now the next one is this one here, is cosine n pi over 6 from n is 0 all the way to infinity. So the defining formula is an is equal to cosine n pi over 6. And then we'll just put all the terms in right now just as is with the cosine, then I'll evaluate it numerically soon using exact trig ratio. So we put the 0 in there, we'll have a cosine 0, then we'll have a cosine of pi over 6 for n is equal to 1. Then we'll have a cosine of 2. Let's leave the 2 over 6 there, or pi over 3. The next one here is going to be cosine 3 pi over 6, and then dot dot dot, keeps going on and on until we get cosine n pi over 6, and then dot dot dot, and then close the bracket. And now to evaluate this numerically, just for completeness sake, let's just first recall the exact trig ratios, and we'll do that by the equilateral triangle. So we'll have this like this. So I'll do this sides are 2, 2, and this can be 1, 1, like that. It's just equilateral. So the equilateral, the angles sum up to 180 or 60 in each, so 666 across, or in radians it's going to be pi, so pi over 3. The whole thing sums up to pi, so pi over 3, like that. And then this one's going to be, well, pi over 6, divide that in 2. Pi over 6. Like that. So then the height here, this is just going to be square root 3, and you can recall Pythagorean theorem. Let's write this better. And then what we should have is, well, the square root of this side 1 squared plus square from the then plus this side squared of a right angle triangle has to equal to, this will just be 1 plus square root 3 squared. It's going to be 3. This equals to 4. In other words, this is equals to 2 squared. So yeah, this is 2 squared. So that's a hypotenuse squared equals to the sum of the sides squared. And yeah, that's correct. And then recall that cosine. Cosine, we'll just look at these two numbers first. We'll look at this and this one. The other one we'll find it by graphing. So what we have is cosine pi over 6, that's this right here, is equal to, well, remember, just adjacent over hypotenuse. So it equals to square root 3 over 2. So adjacent over hypotenuse. So that's equals to square root 3 over 2. Yeah, so I'll just circle this one, just indicate that we got this point. So the next one is now, well, cosine 2 pi over 6. This just equals to, well, cosine pi over 3. So the 2 cancels with the 6, which is 2 times 3. So what we have is this equals to, now we look at the adjacent of this one. There's the angle pi over 3, so 1 and 2. Adjacent over hypotenuse, 1 over 2. Like that. And now what we need to do is get these 2 points. Cosine 0, cosine 3 pi over 6, which is just cosine pi over 2. And again, recall the graph of a cosine curve. Looks like this. Theta cosine theta, and it just goes down and up like that. And so on, there's 0, this point is 1, this is going to be pi over 2. At this bottom peak is going to be negative pi, I mean pi, not negative pi. And then this one's going to be 3 pi over 2, and then it repeats the period of 2 pi, like that. So then at this point right here, this is just cosine 0. That just equals to 1. Then here, this is just cosine, well, 3 pi over 6. Where this cosine 3 pi over 6 is just cosine, well, pi over 2. 3 and 6 cancel out. So what we have is this, that's just equals 0. Like that. So we got this point and we got this point. So there we go. We go from a 0, this is going to be 1, this is going to be square root 3 over 2, this is going to be 1 over 2, and then we have 0. Like that. So, yes, so that's what we have is, putting this all together, we have, thus, put the terms in together, we have 1 square root 3 over 2, 1 over 2, and then 0, and then dot, 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 all the way until cosine n pi over 6, and dot, 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 and keeps going on like that. And I'll just circle this answer like that. So there it is. And now let's look at another example, example 2, and it states find a formula for the general term an of the sequence, and we're given 3, 5, then negative 4 over 25, then 5 over 125, then negative 6 over 625, then 7 over 3, 125. Notice the 5s, notice the switching of the signs, and assuming that the pattern of the first few terms continues. So let's look at this. Note the pattern. So note the pattern of the sequence. What we have is a1 is equal to, well, this one here, notice that if this is the first term, notice how it goes from 3, 4, 5, 6, 7. So in other words, if that's the first term and it's positive, so what we'll have is, I'll write positive, then it's the first term plus 2. This one's going to be the second term plus 2. This one's the third term plus 2. And it keeps going on. This is going to be 5. Notice 5, in other words, 5 to the power of 1. And then this one is going to be, and then a2 is going to be, this one's going to be negative, and then we have a negative, then the second term is 2 plus 2. So 2 plus 2, notice the exact same 2 there. And then divided by, now it's 5 times 5. That's just 5 squared. And then the next one is, well, a 3. This is going to be positive now, so plus 3, this term, plus 2. Divide this by, then that's going to be 5 to the power of 3, because that's just 5 times 25 is that. So we already have 5, 3 like that. And then the last, well, one more term, let's get the fourth one. We have now a 4 equals to now a negative, and then it's going to be 4 plus 2. 4 plus 2. And then this is going to be, well, that's just going to be 125 times 5. So notice if you times by 2, we get to 250. Times that by another 2, we'll get 500. So then we have 2 and 2, that's 4. And then plus 125, that's going to be 625. So in other words, we did multiply this by 5. So we have, this is going to be, that's 5 to the power of 3, add another 5. So at 5 to the power of 4, like that. And now I want to make a note. So note, what we have is, note, if we have negative 1 to the power of 1, this equals to, well, negative 1. But this starts at the first term. Thus, yeah, I mean, but the first term is a positive, not negative. So it's there. So thus, we start with negative 1 to the power of 0, which equals to 1, or equals positive 1. Or we could write this as negative 1, and then if we start with 1 like that, we'll have a 1 minus 1, which equals to negative 1. 0 equals to 1. And we could also do a plus, that it doesn't matter, actually. We could even write that down, plus or minus. Yeah, so this put a note as well here, plus or minus 1 works. So we'll have 1. And because, if you add a plus will be a 2, then it'll be an even number, and then that's just going to make it positive initially. So yeah, just put that there. It works like that as well. But we'll just stick with this one here. So thus, the pattern, an is going to be equal to, well, -1, and then we'll just have this one 1 minus 1, or n minus 1, because that's just for the first term, n minus 1, then we have n plus 2, and then all divided by 5 to power of, well, 1, 1, there's 2, 2, so n. Like that. And now let's look at another example. On notation, here is example 3, and it states here are some sequences that don't have a simple defining equation, and we're given A, where it's the sequence Pn, where Pn is the population of the world as of January 1 in the year n. So yeah, it's gonna not have a simple defining one. You could probably get one or fit a model to the population growth or decay. But if we, and then part B is if we let an be the digit in the nth decimal place of the number e, which is number e is 2.7182818, keeps going on, then an is a well-defined sequence whose first terms are 7182, yes, there's a 7182, 81, 82, 84845, etc. So that's defined based on the number e. So that's a sequence there. And also now, a very interesting one, the Fibonacci sequence Fn is defined recursively by the conditions, and recursively just means you're repeating over and over again. It's done by the conditions. F1 equals to 1, and then F2 equals to 1. And yeah, but I believe in computer science, modern computer science, they can also start with F1 equals to 0. And then F2 is equal to 1. But anyways, we'll just do the original. So then the next terms after that, so Fn is going to be Fn minus 1, so this one, plus the other term. So always the previous two terms. Fn minus 2, and this is for n is greater than or equal to 3. So yes, I'll be exploring more about this Fibonacci sequence later videos. And yeah, each term is the sum of the two preceding terms, so we could just easily write these terms down. So the first few terms are, so we have initially, we have the first term, F1 is 1, the second term, F2 is 1, and then the third term, we just add the previous two. So 1 plus 1 is going to be 2, so then we throw this over there. It's going to be 2, and then add these up, this is going to be, well, 3, and then throw this over there. That's going to be 3. Then likewise, this one is going to be 5, and then 5 plus 3 is going to be 8, and then 8 plus 5 is 13. 13 plus 8 is going to be 21, and then, well, so on. Like that. Keeps going on and on. It's very, very interesting. And yeah, this sequence arose when the 13th century Italian mathematician known as Fibonacci solved a problem concerning the breeding of rabbits. And I go over this problem in exercise 4 at the end of this video, as well as cover briefly on Fibonacci's life, so stay tuned for that further down below.